Good morning, Leonie. Lonnie, good morning, Lonnie. Sorry for the delay. Did you have to do an update as well?
No, I think mine might have just done it automatically when I turned the Chromebook on.
Oh, okay. All right, good. So I had to do my update. Anyways, good morning. How are you?
Pretty good. Just
Yeah.
woke up, but I got my coffee and I'm totally ready
Me
to
too.
discuss the universe.
All right, good. Leonie, you have your coffee?
I wish.
Are you ready to go? Okay.
Yeah, still ready.
All right. So we'll just wait one more minute. I was a little delayed there. So anyways, so you guys read chapter 9, right?
Yeah.
Okay, good. Did you find anything new in there? And Leona, okay, this is you guys are my my core here. I know that you got the message, so probably other people did as well. And I've got Paul on YouTube. Hey, Paul, good morning. And remember, you can ask questions here. And I got somebody else. I don't know who's here, but if you guys say hello, so I can see that you're here. That way I know who's actually watching. It's fine that if you don't want to, but it's nice to know who's here. So we have a little, let's see what I'm going to do. Speaker view, gallery view, speaker view. And I got to pin my video, right? It doesn't matter actually, does it? No, it doesn't matter. When I share screen, you guys can decide what you want to see. Okay, I keep forgetting that. Anyways, so I will go ahead and turn my camera on here. Hello. All right, so we are going to talk about the arrows of time today, chapter 9. Before I do that, I just wanted to shift over to Canvas for a moment and take a look at some things that we were supposed to be doing. So a number of you did the assignment on Monday, which was to get involved in the discussion section. I have to put up your points, but I did look at your questions this morning and comments. And I just want to kind of flip back to that for a moment. So in case you were confused about what you had to do, this was due today, but actually it's not due until midnight. So you still have time, but please do this. So if you click on discussion topics right here, you get over to, what the heck? How did that happen? I do not understand that. What? That's too funny. What? Okay, I put the wrong link there, obviously. Anyways, click. It looks like the right link. Anyways, I don't understand it. Okay, so if you look in here, you can actually see people's comments. I don't know what this means. Unsubscribe. Oh, well, I want to subscribe. I want to subscribe to all these things. These are cool. I'm subscribing. Okay, so you can actually see how many people have commented. And if I click in here, I can actually see the comments, I think. Can I? Oh, I have to click here. Okay, so this was me. I was just, oh, I guess I made it. Okay. So Lonnie made a comment. He said in this inflationary model, I should let him just read, right? That's okay. Let me just read it. The universe expanded quickly and symmetrically without cooling down, being kept in a super cooled state. When symmetry started to break, bubbles would form, which released energy, right? That was one of the questions you had to think about. The formation of a bubble, the phase change always releases energy. And in fact, yes, that energy did have an anti-gravitational effect. And it wasn't enough to go back to the symmetric state, because there's always just it's now spread out. There's not enough energy concentration to do that anymore. But he claimed that that would allow the universe to continue expanding at just this critical rate. And Leona put the bubbles would be extremely large in size. Yes, they could be. In fact, there could be many bubbles. We don't know. We don't have access to those other bubbles. But on what it showed was, yeah, you guys are answering the questions actually, that if there was one giant bubble, that the symmetry breaking would take place very slowly. So, and then Hawking said, in fact, it would have to be broken everywhere in every bubble at the same time. So blah, blah, blah. Okay, so that's great. And then Elvis had some questions. He was confused about the path integral. And you're right, we only are given 3 paths, but in fact, every possible path is allowed. And then I showed you guys the Wikipedia article, which is kind of interesting. Wikipedia and Wick rotation. That's funny. I just noticed that. But it's called the Wick rotation when you change from real to imaginary time. I have never discussed that with students before. This is kind of a fun thing that you guys get to see. And then what happens is it changes to Euclidean. So what happens is whether using real or imaginary time, the Feynman path integral takes every possible path. So that's actually a spatial path, but along that spatial path, the time is acting as a phase, right? The change from real to imaginary changes the equation, so time no longer looks different than space, right? So the x, y, z that you and I would consider spatial coordinates, and t, which is a time coordinate, usually acts a little bit different, right? So when time is a real quantity, the property of time is to change the phase of the wave, right? So if you watch a wave being made, there's a high and there's a low, and there's a high and a low. And this is the phase of the wave, and time is the thing that controls the phase. But when time becomes imaginary, that changes, and it actually becomes exactly equivalent to space. So space and time are no different from each other. So then you get this thing where space-time behaves Euclidean. Okay, so that concept that it obeys the Pythagorean theorem. So if you have not put a comment, Hawking and God, this is Julian. Julian made a comment about the idea that she said, one thing I found interesting, blah, 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 is that there's no boundary condition. The beginning of the universe and the end of the universe are just perceptions that we have as humans. And in fact, time is wrapping around a sphere. You could think of it as a giant sphere. And then there's no beginning or an end. That's great. And Hawking probably didn't believe in God, but he doesn't describe where all this comes from, right? And so Julian says, in fact, that's a more beautiful idea, that maybe that God is the one that created all of this. Well, she didn't say that actually, but anyways, I believe that that you can go ahead and have that idea, and that's fine. Actually, that's perfectly fine for me. In fact, Hawking totally does not discuss where everything comes from, right? He still says, oh, it's just been here. But that's kind of sorry, it's a little weak. You just replaced one question with another. And then we have, that's it. Okay, so a number of you did not respond, which means that you don't have credit, which is half of your participation points for Monday. Those of you who did respond, I'm going to give you those points. The rest of you, I need to see it by midnight, which is kind of late. I don't know why I put midnight, but please today, otherwise you don't get those points. You only get half the participation points. So please complete that. Today's participation points are just going to be a quiz that you take after the lecture, and I haven't finished making it, but I will make it. And today's lecture is on the arrows of time, chapter 9. So let's see, I have a chat window and I have a YouTube chat window. Can somebody tell me how many arrows of time there are? Number one, how many arrows of time? Is there just one arrow of time? And if so, what is it? Okay, so, all right. Hopefully we all know the answer to this question. I'm looking on my YouTube here. Paul, do you know the answer? How many arrows of time? And whoever else is watching, how many arrows of time? Let's get everybody to answer. Yes. Okay, I've got answers from my Zoom group is very vocal here. Everybody on Zoom has answered the question. My YouTubers, I'm still waiting for you guys to respond. How many arrows of time? And I have 2 people watching, so what's the answer? Anybody? No answers. There's no reply at all. That's a song from Phil Collins. Oh, good. Oh my gosh, Leonie's already giving me the next question. Not 3 factorial. Okay, we got a joke here. Okay, so thank you for the joke. 3 is correct. That is correct, Paul. Great, thank you so much. Okay, and the other invisible person watching, you didn't want to respond. It would be nice if you could, because then I could see. You got me. Okay, so actually, Lonnie, in being in his excitement, and I also feel excited about this, he put 3 with an exclamation point. That technically means 3 factorial, which is 3 times 2 times 1, which is 6, and that's not the answer. But I know what he meant. We know what he meant. It's a big joke. Okay, so there are 3, and I already got an answer from Leonie. What are the names of the 3 arrows of time? And since we want to make sure that everybody's on board, let's go ahead and write them down. There are 3 arrows of time. This is a lecture, right? So if you didn't read the book, shame on you. You need to know this. 3 arrows of time. And what are they, right? There's 3 of them. There is the thermodynamic arrow of time. There is a psychological arrow of time, human arrow of time, if you will. And there is a cosmological arrow of time. And you need to know why these are considered to be arrows of time, and what do they mean? What's going on? And I'm sure actually if you did the reading, you probably already understand. Even though there are 3, there's something that we want to be able to talk about. Are they all going in the same direction? Do they all agree with each other, or do you see problems with them, right? So actually Hawking describes in this chapter, one of his misunderstandings about time. And I think that's really kind of important for you to understand, is that we don't understand immediately what's going on because, this is the universe. How do we understand this strange and wonderful thing? And the answer is, well, some things are understandable, and that's kind of strange. Why should it be understandable? That's actually a question I have for you. Why should the universe be something that you and I can understand? Why? How is that possible? What the heck is intelligence? Okay, and the answer is, I'm just kidding. Sorry, there's no answer here. And so if you think about what intelligence means, what does it mean to have intelligence? Are there other intelligent beings in the universe? And of course, the answer is yes. And the nearest intelligent beings are, I don't know, but they might be here, right? I mean, are we intelligent, actually? I'm just kidding. That's actually a pessimistic view of humanity. I actually have a more optimistic view. I believe that human beings, have some intelligence. I think we're going to get more intelligent over time. But right now, the intelligence that we perceive is not as much as it will be. I think we will be more intelligent in the future, and hopefully, and we'll be good for it. We're going to get out of this whole coronavirus mess and be more intelligent, right? Because we're taking classes. All right, blah, blah, blah. Talking. Does anybody want to speak? Somebody want to give us a brief definition? Why is there a thermodynamic arrow of time? What exactly is the thermodynamic arrow of time, and what does it have to do with? Anybody know that one? How about one of my Zoom people? I can hear from you.
Okay, I'd love to try to explain it. The thermodynamic arrow of time is the arrow of time that points in the direction of the increase of entropy in the universe.
Okay, very good. That was very clearly stated. And so thermodynamics, of course, arrow, I like the way you said that, points in the direction of increasing entropy. Oh, I don't know why I'm capitalizing it, because because the word entropy is kind of cool. That's why, no other reason. I probably am not supposed to capitalize it. Any English majors, I probably should just, anyways, whatever. I don't know what to say. Absolutely, yes, that is correct. Okay, so this, let's talk about that. I mean, that's kind of a weird, actually, I don't know if it's weird. It says, the laws of thermodynamics say what about entropy? That the entropy of the universe can only increase. It could stay the same. Sorry, it could stay the same or increase, but it cannot go down, right? It cannot go down. So it would be, what does that mean? Why, right? Why would that be? So I'm wondering, just because, I don't have a lot of, lecture material prepared. Usually I would just be talking to you guys and trying to demonstrate things. But there is a really wonderful, weird movie. Hold on, before I do that, I want to see if I can find something. I wonder if I can. That would be so cool if I could, right? Okay, let's see. Oh, awesome. Okay, so I was looking on YouTube, and of course, if you go looking, you can find anything you want. And so I love this. This is so funny. Oh my gosh, I love this. Okay, so I want to talk about entropy, and if I were in class, I wouldn't do this necessarily, but I would discuss this. But I want to take you to YouTube, right? Here I am on YouTube. I've muted the sound. But this is somebody smashing a coffee mug. Ready? Smashed. Okay, so what just happened? Let's see, they do it again. Oh, slow motion. I love it. Oh my God, how gratuitous is this? Okay. Oh my gosh, okay. So using the magic of YouTube, I have found a video showing someone, let's do it again, right? Smashing, there's a smashing of a coffee mug. So as you watch, right, as the coffee mug goes flying through the air, right, it goes from a state of being organized, right? It's like, oh, I can change the speed here. I can actually go really slow, right? Here we go. There we go. I want to see that coffee mug. The coffee mug is whole, right? It's organized. All the pieces are together. What would you say about its state of entropy? Is it a high or low state of entropy when it's a whole thing? Anybody from my talking crowd? Actually, oh, there we go. The chat says, oh, I can't see. I don't know what I'm doing. I have to minimize and I have to look at the chat window. And you said low. Okay, great. That's exactly right. So when it's whole, right? When the coffee mug is whole, it is a, oh, they did more than one. This is actually a second video. Gosh, that's so funny. So, but that's fine. This is a whole mug. It has low entropy state. When it smashes, all of those pieces goes flying in every direction. and we have a state of higher entropy. These greater number of pieces somehow reflect the evolution of the cup's state of being, right? So when we watch the universe, we see this happening spontaneously around us. The universe evolves from a state of lower entropy into a state of higher entropy. Now, a human being obviously helped this to happen. So the one thing that you want to talk about is, have you ever seen this? Have you ever seen a coffee mug reassemble itself? Okay, it doesn't really work. I want to really, you know what it should, oh man, I just realized what I really want to do. I don't want a YouTube video. I want a GIF. Where is it? Yeah, let's see if I can do this. No, that didn't work. Okay. I want a coffee mug. I'm sure I should find something wrong. Oh, this is not. Oh, that's wild. What the? Cool. This is not. Oh, that's not right. Okay. Oh, This is cool. I love wasting your time. Sorry about that. Anyways, yeah, I can't find it. I need to make one. That's what I should do. Oh, here we go. This is it. There we go. You see that? That's actually exactly what I wanted to talk about. Have you ever seen that happen? Anybody ever seen that happen? Something broken spontaneously went back together again? Anybody ever seen that? And the answer is no, you've never seen that. You would be a little bit disturbed, right? Now, I actually want to discuss that for a moment. I want to ask you if you can imagine that happening. Can you imagine a coffee cup going back together and reforming into a whole? Can you imagine that happening? I don't know how you would make that happen. How could you make that happen? Is it possible to repair the cup? What do you think? Okay,
You can
so
see
let's.
the smallest of pieces that you'd never be able to find, like that small grain, and fix that part back. So you can never
Okay.
quite fix it the same as just putting it back together with reversed.
Okay, so you've already made some assumptions. First of all, that you're saying that somehow I'm not careful enough to find every little tiny piece of the cup. And Lonnie, you know that I'm going to make it possible, right? I'm going to break the cup in a box with a very fine scale underneath, so that I know if there's even a grain of this cup left over. Could I make it, do you think, let me ask you a question. Do you think I could make it so that it would be imperceptible for you to even know that it was broken?
Okay, yeah.
Yeah, okay. Actually, totally random. Has anybody ever heard of the Japanese art of repairing broken things?
Yes.
Have you heard of it?
Yeah, they do it with gold.
It's called kintsugi, right? Have you heard of that?
Yeah.
Oh, I love this. Actually, so one of my favorite bands, Death Cab for Cutie, put out an album a couple years ago called Kintsugi. And I knew about this before, but I just think it's very beautiful as a philosophy. And Kintsugi, it actually, they break it on purpose, but then they repair it. And the repairing is done in such a way so that you can see that it was repaired. But in the Japanese culture, this is considered more beautiful. And I actually kind of agree. I really like it a lot. So they use pieces of gold, or they do some, it's quite obvious that this piece is repaired. This other one, I think they have a number of pictures. This one, oh yeah, you can't see it so well. I don't like that one. But this one, look at this, right? They use this beautiful gold to put the pieces together. And actually, it's kind of like, imagine a person, right? In our lives, sometimes we get broken, right? Things happen that make us feel very unhappy and sad. And then, you put your life back together again, right? Things happen that allow you to reform. And it's those experiences are part of who you are. And I think that's a very beautiful idea, that, this pottery will never be the same again, right? It won't be whole and perfect again, but in some ways it's more beautiful. And so that philosophy, I think, is beautiful. Actually, I think, by the way, that this fully supports the growth mindset. If you don't have a growth mindset, then you can learn to adopt a growth mindset and know that everything that happens to you in life is part of who you are. And sometimes those events are not great, but the way that you approach life lets you reform the experience and let it be a positive influence on you, right? So the things that you made a mistake, you turn it around and figure out a way to make it better, right? So I'm going to learn from my mistake, and the next time I won't make that mistake again. So anyways, that was a little bit of a side path, but that's what this class is about. Okay, so and I want to have a little fun. Why not? So instead of just lecture, this is my lecture. This is what I do. So I wanted you to talk about kintsugi, right? So kintsugi is something where it's very obvious, right? So clearly I didn't put it back in the exact same state that it was before. I clearly did not make the entropy the same, low entropy. But let's suppose that I did, right? Suppose that I was able to reset the cup and make it look exactly the same? Actually, could I make a new cup, right? Could I make a new cup that's nearly identical to the first cup, right? And the answer is, of course I could. But maybe somebody can explain to me how that I didn't actually reset the cup. Why is that not exactly resetting the cup? Putting it back to where it started. If I make a new cup.
All right, I got a good one for this too.
Okay.
The effort required for you to either put the cup back together or make a new one, just the work you put in adds more entropy to the total universe than the
Okay,
work you
that's
gain.
perfect. Okay, once again, great. Thank you, Lonnie. Does everybody understand that? So although I could lower locally the entropy of a system and make it look as though it is a lower entropy system, what it actually is, sorry, I can locally decrease entropy, that the overall increase in entropy of the universe is still positive, right? There's an increase in the entropy because of the work that I did. I heat up the air molecules around me. I, produce waste, whatever I breathe into the atmosphere. Somehow I produced more entropy in that process. So you can't get around the laws of thermodynamics. If you saw a spontaneous decrease in entropy, you would be confused. It's not something that happens. And so, yeah, anyways, so the arrow of entropic time or arrow of thermodynamic time points in the direction where things become more disorganized, right? The entropy of the universe goes up. And so, yeah, that's very confusing. Now, did anybody read Stephen Hawking's initial idea? He said, what if the universe expands for a while and then contracts? What did he think would happen? Oh shoot, you know what, I'm getting ahead of myself. But what did I'm going to ask it anyways. Let me ask it now. What did he think would happen to the entropy of the universe if it started to consolidate? Anybody remember?
So the arrow for entropy would turn around once contraction started.
So he thought that if the universe began contracting, that in fact we would see the universe getting more organized. It would be less entropic. And so what would be natural in those times would be things spontaneously coming back together again. That would be a natural thing for us to observe, the things going from pieces back into whole, right? He was wrong, okay? And he recognized later that that's just, come on, that's crazy. Stephen Hawking, you're crazy. Oh my gosh. Has anybody seen that rap battle between Stephen Hawking and Isaac Newton, by the way? Anybody seen that? That's totally not relevant, but it's just funny that they have such a thing. Anybody seen it? Anybody? Okay, I'm not gonna show you now. That's just wrong. I'm not gonna do that unless we have extra time at the end, and then we can talk about it. Okay, all right. So we've dealt with thermodynamic arrow of time. It says that the universe has to get more disordered, the entropy has to go up, and the arrow of time is pointed in that direction, right, towards a greater entropy. Okay, so what about our second arrow of time? Let's go ahead and talk about that. So our second arrow of time is psychological. So what does it mean? What's the psychological arrow of time? So how about, can I get one of Leonie or Leona to respond? Because Lonnie has been more vocal. Sorry, not that I don't want to hear from you, Lonnie. I just was hoping to hear from one of the other people in the class. Leona.
Psychological arrow is the direction in which we feel time pass.
Okay, so what does that mean? Don't turn off your mic. What does that mean? We feel time pass.
We can remember the past, but we don't know what's going to happen in the future.
Okay, that's really a nice, concise way to talk about it, right? Do you remember what you're going to do tomorrow? It's like, that's a ridiculous thing to say. Actually, why don't you ask somebody that? They'll be like, what? What do you mean? What if you could remember tomorrow? What would that mean, right? So I know what's going to happen tomorrow, but then what would be the problem? I wouldn't know what happened to me yesterday, right? Well, the concept of tomorrow and yesterday are based on our concept of the arrow of time, right? The psychological arrow is our human perception of time. So let's write this down as if I were in the classroom. So here we go. So we have our oh, I figured out, I don't think you guys will have the camera fading in and out of focus anymore because I told it not to refocus. Isn't that cool? Things just keep getting better. Okay. Psychological. Okay, psychological arrow, right? What is it? It is the direction that we experience time, the direction that we experience time passing. And actually, I really like the way Leona said that. We can remember our past, but not our future. Okay, so again, I don't know what else to do with you because this is a pretty quick little chapter. There are some really great things to talk about, and we will. But I do want to throw in a couple of little side ideas. So let me ask, first of all, would you like to know the future? Would you like to know what's going to happen to you tomorrow? Would you be interested in finding out what's going to happen tomorrow? Anybody interested in that? Raise your hand if you would like to. You guys can raise hands, by the way, and things like that. And if you don't want to talk, you can actually you on your participate. If you look on your participation, you can say yes, no. You can say thumbs up. You can do all your reactions. You can do all kinds of things like that. So would anybody like to? Oh yeah, you'd like to know what's going to happen tomorrow, Leonie. Okay. So what would you do if you knew what's going to happen tomorrow? What would you do? You'd like to do that. Okay. Oh, she's practicing. Okay. She's yeah, she's waving and she's putting the thumbs up. What would you do if you could know tomorrow?
The thing is, if I know tomorrow, there's no like surprise, that there are no surprises anymore, which is kind of sad. But still, we could.
Wait a second. You said you wanted to know, but now you just said you'd be sad. Okay.
Yeah,
But
well,
you want-
maybe the near future, but not the future, because it.
Oh,
Yeah, I don't want to know everything like when I die. Or,
yeah.
I don't know.
Actually, if you knew the future, what would it mean about you as an intelligent being?
I
Would it
had
mean
no choice anymore, kind of.
exactly? So I have to say that as much as I might like to know the future of humanity and the future of maybe even my own life, you know, the day I'm going to die, I don't really want to know that. You know, because what it means then is it would change, it would have an influence on the way that I lived my life. And maybe even would mean that I have no more free will. And I don't see the point in being alive if we don't have free will. It doesn't make much sense to me. I don't want to just be a bacterium that is fermenting in a cell and doing whatever it's being told to do because of biology, right? That somehow our brain gives us the options to change, right? I don't know what I'm about to say. I'm thinking and I'm living my life, and I haven't planned every moment, and I like that. I think that's wonderful. I didn't know that I was about to say that, right? I think that there's something kind of wonderful in the surprise of what we discover in life. And if we knew the future, then you're right, there would be no surprises. I would be sad. I would be sad as well. So has anybody seen the movie Benjamin Button? The Remarkable Life of Benjamin Button?
Oh yeah, that was a great movie.
Have you seen that one? Okay, so let me see. So anybody not seen that movie?
I haven't seen it.
Okay, do you know what it's about by any chance?
No.
Okay, let me see if I can find a little clip of that actually. Maybe you'll want to watch it now that you're The Curious Case, that's what it is. The Curious Case of Benjamin Button. And I probably could find a little trailer. Let me just pause for 1 second. Hold on. Oh, skip the ad. Okay. All right. So I have a oops. Pause. All right. Okay, so I'm not sure if this is going to work. I think it's going to work, but if you guys can't hear the sound, just go look it up yourself. But I am going to click over to a little YouTube clip for The Curious Case of Benjamin Button. And now I can't see my play button. There we go.
My name is Benjamin Button, and I was born under unusual circumstances. While everybody else was aging, I was getting younger, all alone. Only on the outside.
Okay, so this is a very strange idea, right? That this guy, he lives his life backwards. He starts off as an old man, and then as time progresses, he becomes younger and younger and younger. So it's kind of a funny idea. Anyways, so the psychological arrow of time, right? We experience time in a way that we have events that happened in the past. And by the way, actually, when is now? To stop and think about that for a second, right? By the time you say now has already passed, and now we're talking about things that happened in the past. Actually, our perception of time is very strange. We mentioned last class that in quantum physics, it's probably going to be true that time is not continuous. It has a smallest step. And even if we tried, we cannot, the feeling that time is passing feels continuous to us, right? I can't sense a moment when I didn't exist. But the reality is that time is really probably more like a movie. Time is like a series of steps, and we experience it as continuous, right? When you watch a movie, it looks like everything is moving, but it's an illusion, right? The movie is a series of still frames that when played together gives you the feeling of motion. But the thing about a movie is you could play it forward or backwards, right? Can we do that with our life? And the answer is no. I don't know. Can we? Can we go back in time? Is it possible? Anybody?
Oh,
Do
not
we ever-
yet.
Not yet. Okay. No? So what happens when you remember?
Yeah, we go back in time in our brains, but not
In our brains? Yeah, somehow it's not
physically.
really external. Yeah, we don't really go back in our physical body. But what is the most important part of being human? I don't know. I mean, I actually don't know. I don't know where our consciousness rests. I mean, I actually don't even know for sure, even though it seems likely that that's the case, that our consciousness resides within this physical body. I don't know that, right? Okay, so I do want to mention to you that yeah, we don't experience going back in time, and yet we can remember things. Is that the same thing? Probably not, right? It's more passive.
I always thought remembering things was more like bringing the past to you rather than going back to the past.
Oh, okay. Right. Well, so actually that's a good point, because when we think of the past, it's then through the lens of our experiences, right? So it's not really the past anymore. It's somehow a new version that we see with the experience of our life, right? So you can look back on an experience and try to understand it, you know, for yourself. And that changes over time. I'm speaking to you as a 52-year-old man. So as I've lived my life, right, the way that I looked at my life has changed too, right? I reflect back and I'm gentler than I used to be, right? Less critical of myself. I have a growth mindset now. But anyways, I didn't always have a growth mindset. And so if you don't have a growth mindset, think about adopting it, because you will enjoy life more and you will forgive yourself and be human and allow yourself to make mistakes and learn from them always, right? So anyways, that's a side topic. Okay, so we got off on a little tangent, but psychological arrow of time is the arrow of time which talks about the flow of time that we experience, the way that we remember our past, but not our future, right? And we agree that it would be kind of strange if we could know the future, right? That would be maybe even something, you know, you kind of want it, but then you don't want it, right? So personally, I don't want it. I don't want it. I like the novelty. It's like probably why we like to travel and why I want to go to space and why I want to live forever, you know. I can see all this new wonderful things that a human lifespan is too short to see, right? What if you could watch stars being born and stars dying? You know, you could see that all happening. You know, what if your human life could encompass that? Is there a way? And right now, the only answer is to simulate it and speed it up and make it fit into a human life, because we don't live long enough. But maybe, you know, there are some intelligences that live much, much longer, right? So for example, trees can live hundreds and hundreds of years, maybe even 1,000 years. What if we were trees? You know, how would we experience? All right, we're getting off on a tangent, never mind. Okay, so let's get to our third arrow of time. Our third arrow of time is, let's see, I heard from Lonnie, I heard from Leonie. What is our third arrow of time? Or Paul, if you want to jump in. What is our third arrow of time? Okay, so
Oh.
God knows.
Sorry. Oh,
The cosmological. Okay, you gave me the
It's-
whole. I know you gave me the whole list, but
it's the
so what does it mean?
cosmological.
Yeah.
It's just the cosmological arrow of time should point in the direction of the universe expansion.
Okay.
So it
So-
can be linked to the thermodynamic arrow. So because the universe is heading towards maybe heat death, or just
Okay.
because it's expanding.
Good point. Right. Okay. So the cosmological arrow, you said that very well, points in the direction of the universe expanding. Okay. So in fact, if we saw the universe contract now, okay. So actually, that's fine. So the cosmological arrow points in the direction of the universe expanding. We see the universe expanding, and you said that this is the same direction as the thermodynamic arrow. Well, what about the psychological arrow? Would you say it's the same direction or not?
I would say so, but I'm.
Well, why don't we talk a little bit about how the psychological arrow and the thermodynamic arrow fit together? Do they go together?
Yeah, they go together. So
They
I
go
guess
together, right?
if
It would be-
the other ones, the thermodynamic and the cosmological go together, they all have to
So
go together.
I think you were kind of alluding to the idea that because cosmological and thermodynamic have to be the same direction, we actually already discussed the idea that the thermodynamic and the psychological have to be the same direction. In fact, Hawking would say that we see all the arrows pointing in the same direction. And so that's an important thing to just make sure we note, right? We see them pointed. There are three different arrows, 3 different topics, but somehow it wouldn't make any sense. If one of them was pointed in the wrong direction, we would feel like that doesn't work, right? It doesn't make any sense. Our intelligence seems to indicate that these should all be in the same direction, so that it, it's the only thing that makes any sense. But he was at this time under the he did not know what would happen to the future of the universe, right? So one of the scenarios that Friedman described is that the universe expands and then contracts again, right? If the total energy of the universe is negative, then we would expect this to happen. Now, actually, I love, I should have talked more about this. I love Hawking's discussion of energy. I love it. He really does actually describe positive and negative energy correctly. I just, in the chapter on Hawking radiation, I don't think he describes it very well, but he does describe it a little bit later. And he talks about how gravitational attraction leads to a gravitational potential energy, which is a negative energy. It's a negative energy. And if you were confused about that, please write that down, because that's the negative energy that is important, right? We have positive energy. Positive energy. What kind of positive energy do we have? Well, actually, matter is a form of positive energy. Matter. Kinetic energy is always positive, right? These are a couple of positive quantities. There's even more. I mean, thermal is inside of that. Matter, positive energy. But then there's negative energy. And the negative energy is going to be the gravitational potential. Gravitational potential energy. That's negative energy. And when you consider the two of them together, what's the answer? What do you get if you put this positive and this negative together? Well, he said it's very close to 0. In fact, it might be 0. And if it's 0, then the total energy of the universe is 0. Okay, so what happens when you make the universe twice as big? All right, what's 2 times 0? Well, it's a bigger 0. It's still 0. And you can see that we have no problem. Conservation of energy is fine, right? It's still 0, no problem. 0 plus 0 plus 0 plus, we just got a big 0. But what it means is, right, that if you have a 0 energy, we actually described what it means is the universe is going to expand to infinity and then stop, right? But maybe there's just a little bit more negative energy than positive energy, right? There's just a little bit more binding energy. And what does that mean? The universe will recollapse again, right? He didn't know. On the other hand, maybe there's a little more positive energy, in which case the universe will expand forever, and then we will get that heat death of the universe. Okay, so let's pretend from Hawking's point of view that we don't really know what the right answer is. And just naively, we want to talk about his big mistake, right? What happens if the universe collapses, begins to collapse? Okay, so what are the consequences of the universe collapsing? What happens to the arrows of time in that case, right? So this is why he was getting confused, right? What happens to the let's start with the cosmological. What happens to the cosmological arrow, right? The universe begins to collapse. Now what? Right? Cosmological arrow. Which direction is it pointing? Well, it points towards a smaller universe, right? Not expanding, contracting, contraction. Points towards contraction. So the universe is getting smaller. So then what? Things are getting more organized, right? Here's mistake. This is a mistake. This is wrong, right? Right? He says which one? Sorry, the thermodynamic. thermodynamic arrow, right? What does it point towards? The universe getting more organized. He thought that we would see the universe getting more organized, lower entropy. He was wrong, right? In fact, there's no problem with that. It is not lower entropy. But what if you did? What if you imagined that the thermodynamic arrow pointed towards lower entropy? Now, let's talk about the psychological arrow. What would happen? We already kind of alluded to this before. But what would happen if the universe is getting more ordered and less entropic, lowering entropy? Then what would we see spontaneously? We would see, right? It would be ordinary and not unusual for broken things become whole, right? That would be an ordinary occurrence. That would be a common thing. And so in our minds, right, we would have, it would be ordinary for things to organize. Okay, so I actually left something out. Shoot. All right, I'll go back to that. And so he would still say that they would agree with each other. Now, it turns out there's something wrong with this, right? The mistake is that somebody showed him that in fact you could get a smaller universe that is still incredibly scrambled up, and that somehow information, this is actually what it became later on, cannot be destroyed. And that information or entropy, and actually, is that really true? Information cannot be destroyed. So the disorganized state can actually can exist in a very compact object. It's just incredibly complicated, very, very complicated. And so actually, I guess what I want to tell you about is he found out that it does not have to be, so let's just say the mistake was that the universe can contract without decreasing entropy, right? That was his mistake. He thought that it would have to decrease entropy. That was wrong. And in fact, years later, there's something really interesting. What happens to objects that fall into a black hole okay? What happens to the objects that fall into a black hole? So one of the, this is actually, you know what, I think I should make you guys read this paper, or at least look at it. In fact, I have that on my list of things to do, right? Read Hawking paper on this. It's one of the last papers he wrote about. Actually, not the last, but one of the last couple of years of his life. He was really interested in this topic. What happens to an object that falls into a black hole? Is it destroyed? And is the information that existed when the object was whole, is it gone? And he said, no, right? The information on that object's existence is encoded somehow in the event horizon. It actually has to be there somehow. And that if you had enough technology, or if you were sophisticated enough, you could somehow unravel what the black hole did when it destroyed that object. It somehow kept the information on what the object was, and it encoded it somehow in the event horizon. So anyways, this is what he finally, this is one of the last things that he did before he died. He showed that the information cannot be destroyed. So no matter how organized the universe becomes, the pieces of it that existed before, somehow that information still has to exist. Okay. So yeah, let me see. What else can I talk about here? So we got the three arrows of time. Mostly, I mean, they agree with each other. Oh, so in this chapter, he does describe, see, I'll come back to this here. Let's see, what else does he talk about? He talks a little bit about, oh, this is really critical. He talks about the anthropic principle again. But actually, before I do that, I want to mention something to you that you're supposed to know, actually. So have you ever seen something spontaneously organize itself? You know, things like a broken cup reassembling into a whole cup. And the answer is you've never seen that, probably, right? And yet nature provides us with opportunities, lots of really crazy things where you know, things spontaneously are organized, right? Of course, another part of the universe has to be disorganized. That's not a problem. But what appears strange to you at first glance, like reassembling a cup, right? That would just be crazy. I mean, how could that happen? But it turns out in nature, things get organized all the time, right? Actually, you can see crystals growing. Crystals are organized. They're lower entropic states than what they came from. And of course, there's another part of the universe that gets a higher entropy state, so that's not a problem. But when we say that things don't spontaneously get organized, it's really not quite right. It turns out it is not only, it happens, but in fact, it happens quite a lot. It's just not something that we usually see on a larger scale. Okay, so I have never seen a broken cup reassemble itself into a whole cup. I've never seen that happen. But I can imagine it, right? I could imagine, I can visualize it in my head. And so I don't want you to listen to me too much, but I'm going to tell you something that that you want to be aware of. And that is when you talk about the Feynman path integral, for example, and you describe any possible thing can happen, right? Anything, it goes from A to B, right? And anything is I put B there and it doesn't matter, okay, wherever A and B are. The path integral says that there's all possible ways can happen, right? If you can imagine something, oops, lost my lights. Okay, if you can imagine a situation, a scenario, it is possible. And from a quantum point of view, what I mean by that is there's a non-zero probability, a non-zero probability of it happening. Okay, so if I could imagine a cup reassembling itself, I don't know how that would happen. I mean, it just seems so random and bizarre. I mean, I don't know, you know, how could that happen? But there must be, you know, there would be an explanation for it. It just is very, very difficult to understand. And somehow I want it to be, you know, something that happens without my intervention or without another human being intervention. But it turns out nature has shown us that things that are strange can happen, right? So I want to build a nuclear, let's build a nuclear power plant, right? And a nuclear power plant is pretty strange thing to build. Why do I want to build that? Well, it turns out that we discovered evidence in nature that nature has done this, right? Nature has made them, and that seems kind of strange. It's not exactly, you know, the kind that we would have today, but in fact, nature has put together a scenario where nuclear material decays, heating water, which turns into steam, which then, you know, does something meaningful. It erupts or, you know, does something like that. And we found evidence of natural nuclear processes. I don't know if I'd call it a power plant. I'm stretching the situation a little bit. But the idea is you can find places where nature has created them. Again, I mentioned like crystals, right? A crystal is an example. And sometimes actually, maybe you've seen large crystals. Actually, there's a cave in Mexico, which I really would like to visit, but it turns out the cave is filled with poisonous gas. I don't know the name of it. Let me tell you. Let me find it. Mexico, Mexico, giant crystals. It's pretty obvious. What is it called? The Cave of the Crystals. Naika. Okay. The Cave of the Crystals. Okay. So let's see if we can take a look. This is how stuff works. I found a website. So in Mexico, this is the Naica. I don't know how to say that. They are gypsum crystals. There's a person, human being, and look at these giant crystals which have formed. Now, the cave is so the massive crystals were after water was pumped out of the cave by a mining company. 2 miners saw the crystals when they entered the drying cave on foot. It is amazing. Okay, so check that out. These are enormous crystals. Massive. They're 984, 300 meters below the surface, below the mountain. And the crystals went through at least 500,000 years of uninterrupted growth. Many are long and wide enough to walk across and look like Superman's Fortress of Solitude, if you've seen that movie. So anyways, it's strange, but it turns out you can find things like this. And those are huge, right? They're not tiny. These are very organized. They're highly organized. Now, obviously, it's not going to be that hard to explain how the entropy still increased. So why is it dangerous? It's really hot. Okay, so what is it? It's super hot, 113 degrees Fahrenheit, high humidity, close to 100. Oh, and so if you stay too long, the water would condense in your lungs. That sounds dangerous. I thought it was other gases. Never mind. Ooh, check this out. They discovered microbial life trapped inside the crystals. Wow. The organisms have laid dormant for up to 50,000 years before they came along. Wow. That is neat. Okay, cool. All right, so random. But these giant crystals are examples of highly organized things. So as unusual as it is, if there's a possibility, then it can happen. But what's going to happen is that it won't happen very often. You could watch for 1,000,000 years and it would never happen, right? It's not going to be something that it's going to happen very frequently. So the probability of the unlikely events is likely small, right? So it doesn't mean that it can't happen. It means that it's unlikely to happen, right? So more often when you see a coffee cup broken, it's because you saw it whole and then became broken. And so the reassembling thing is something that has such a tiny probability, you really are never going to be able to experience it. But it's still there, right? In quantum physics, even the strangest thing may still exist just because I can imagine it, right? It's something that I could almost imagine. Anyways, all right, so that was a little side topic. So what about the arrows of time being together? What does that mean for human life, right? Okay, so he talks about C, P, and T. Remember that we talked about this before. The fact is that C and P and T have all been shown to not have symmetry. So if you reverse them, the universe does not seem to agree. So either any of them are going to be a problem, but all of them together seems to be okay, right? So if you change simultaneously the charge, the parity, and time, make it go backwards, then in fact you can get something that makes sense. Blah, blah, blah. Okay, so I want to talk about the anthropic principle. Where is it? Where's the anthropic principle? Anybody know how this fits with the anthropic principle? I know it's in here. I have to remember where. What is the anthropic principle? There's a weak and a strong, right? Okay. So here's, yeah, he says, suppose, however, that God decided that the universe shouldn't finish up in a state of high order, but that it didn't matter what state it started in. At early times, the universe would probably be in a disordered state. This would mean that disorder would decrease over time. You would see broken cups gathering together and jumping back onto the table. However, any human beings who were observing the cups would be living in a universe in which disorder decreased with time. I shall argue that such beings would have a psychological arrow of time that was backward. That is, they would remember events in the future and not remember events in their past. When the cup is broken, they would not remember it being on the table. But when it was on the table, they would not remember it being on the floor. Oh no, when the cup was broken, they would remember it being on the table. But when it was on the table, they would not remember it being on the floor. That is so weird. Okay. So let's see. I wanted to talk, I'm trying to find it. Anybody know where? Can you find it?
Yeah, I just found it.
Where is it? What page is it?
In our book, it's 155. I'm pretty sure yours is a little different. So it's
Oh yeah, mine's is different. Okay, so it's near the end.
From the end of the chapter.
At the end of the chapter. Okay.
And it
Okay, you
says,
want to read it? Because I can't find it.
On the basis of the weak anthropic principle, conditions in the contracting phase would not be suitable for the existence of intelligent beings. Who could ask the question, why is disorder increasing in the same direction as time, as that in the universe is expanding?
Okay. Okay, great. Okay, so so that's great. Okay, so one can answer this on the basis of the weak anthropic principle. That's enough, right? Conditions in the contracting phase would not be suitable for the existence of intelligent beings. Right. Okay, so actually he's kind of saying that if the universe is going to contract again, what's going to happen is, intelligent life cannot exist. Somehow it's going to fail at that point, right? We exist now, and we're observing the universe expanding, but as soon as it starts to contract, we're going to have a problem. Okay, so actually, oh yeah, there's even more. Okay, so why is disorder decreased? The inflation in the early stages with the no boundary proposal predicts, which the no boundary proposal predicts, means that the universe must be expanding at very close to the critical rate at which it would just avoid recollapse, and so will not recollapse for a very long time. By then, all the stars will have burned out, and the protons and neutrons in them will have probably decayed into light particles and radiation. The universe would be in a state of almost complete disorder. There would be no strong thermodynamic arrow of time. Now that's a new term that he hasn't used before. Okay, so does everybody understand what he means by strong thermodynamic arrow of time? What does that mean? Strong thermodynamic arrow of time. It's a new term. What makes it strong or weak, right?
Maybe
when we can observe what? Go ahead.
Maybe it's not so certain in this postulation here that the universe is going to just be at an increased state by the end. If we don't know what the state of entropy was at the beginning, it could just be constantly a random state of entropy. So it wouldn't be set. It wouldn't be a very strong arrow if it's more randomized entropy.
Yeah. Okay. All right. Pretty close to that. I think it's maybe. So what does he mean? So a strong thermodynamic arrow, right? Namic. Sorry, namic. I forgot how to spell. What does it mean? A strong thermodynamic. So what it means is that there's a clear difference between the initial and final entropy states, right? Okay, so if I see a whole cup and a broken cup, right? It's pretty obvious. But what he's saying is by the end of the universe, that the state is so randomized, like you were saying, that there's almost no difference, right? So the events that I'm going to see are not going to produce very large changes in entropy. So strong means, I guess, really large, a large change in entropy. And he's saying that by the end of everything, right, the heat death of the universe, that it's not possible to make large changes in entropy anymore, right? Because the everything is already so disorganized that, you know, there's not, you know, any changes that you make are going to be small by definition. Okay. So listen to this though. This is actually really kind of important. So disorder couldn't increase much because the universe would be in a state of almost complete disorder already. However, and this is kind of an interesting idea. He's positing an idea, and actually he's not alone. A lot of people have said this or have tried to figure out what's special about intelligent life. But he says a strong thermodynamic arrow is necessary for intelligent life to operate. In order to survive, human beings have to consume food, which is an ordered form of energy, and convert it into heat, which is a disordered form of energy. Thus, intelligent life could not exist in the contracting phase of the universe. This is the explanation of why we observe that the thermodynamic and cosmological arrows of time point in the same direction. It is not that the expansion of the universe causes disorder to increase. Rather, it is the no boundary condition causes disorder to increase and the conditions to be suitable for intelligent life only in the expanding phase. All right, wow. That's pretty important to understand. So if this universe progresses, Hawking has doomed us to eventually have to die, right? There's just no way. Well, assuming the universe, well, actually, no matter what, really, we have a problem. Either in the contracting phase or in the heat death phase, we are going to have a problem where we can't extract entropy anymore, or we can't increase the entropy, which means we can't extract energy from the system anymore. And so he says human beings cannot exist. Now, I actually disagree with him right now. Can anybody think of a reason why I might disagree with him? Because he's making some assumptions, first of all. What are his assumptions? The universe is, anybody see an assumption here? Anybody see an assumption? Okay, so I'm going to say that he assumes that the universe is smeared out and the energy is not concentrated, right? Everything is just kind of spread out. The universe is expanded, the heat death, right? Heat death, the temperature is too small, blah, 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 right? Everything is done, right? Everything is so spread out, blah, 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 right? Okay. But one of the cool things about intelligent beings is they make local entropy decrease, right? So one of the problems with Stephen Hawking is he's not really thinking very big, right? He's thinking of human beings in their current form. But I want you to imagine that in the future, civilizations will have the ability to think big, right? Imagine taking a galaxy-sized cloud, which by itself can do nothing, and then artificially contracting it, right? I mean, at least for a little while, you could do this, right? I don't know where you're going to get the energy from, but don't worry about that yet. Oh, I know where we're going to get it from. Energy of space-time. Okay, we're going to get it from virtual particles that spring into existence. I would argue that in the future beings might have the capability of creating local order, right? And because of that, there will be a difference in the entropic state here versus the rest of the universe, right? So if you have a highly organized state and you have a disorganized state, there's a difference in entropy. And that difference in entropy means that they will be able to exist. It means intelligent life can exist. Now, this may only last for a while, but in his brain, he says when the universe stops making it amenable to human life or to intelligent life, that we have to die. but in fact, I don't agree with him. For a long time, we'll be able to do things like this. The other problem is that he's thinking about human life in the way that it is right now. You have to eat food to exist, right? And it's kind of inefficient, right? Eating food produces a lot of waste, and we don't really get all the energy out of our food that we could. I mean, I think the amount of energy you need to exist is, you know, it's pretty small compared to the amount of food that we eat. We really, you know, a lot of the food that we eat is just water, and we expel that. So we don't actually get anything out of that. What if we stop being, you know, creatures made of flesh and blood, right? What if we become a kind of machine, right? What about a human machine that only needs a tiny little bit of electricity using a small amount? Again, electricity is not perfectly efficient, but in fact, in the future, if we become a machine, I don't know, do you want to be a machine? Does it matter? Are we machines already? A human machine using small amount of electricity instead of food, right? We can become more efficient. I don't actually know. I mean, maybe there's a time when we stop being corporal beings, right? We stop being physical beings, right? Maybe we're no longer physical, right? No longer have a physical body. Is that possible? I don't know. I don't know. Hypothetical. I can think about it. It's a possibility. So anyways, yeah, so according to Hawking, we need the ability to extract energy, which means we need a significant, strong arrow of thermodynamic time. I just disagree with him, but you can agree with him if you want. That's fine with me. Now, I do want to tell you about your homework because I have this fun homework. Our next, you should, by the way, also be reading the next chapter, chapter 10 is going to be really fun. Oh gosh, we are getting ready to talk about string theory. Before we talk about string theory though, I want to introduce you to a concept that's necessary for string theory. So read chapter 10, but that is not the most important thing. The most important thing is to do your homework. And I want to tell you about your homework right now, which is to watch a movie and then respond. There's a little quiz you have to take. Let's see, I'm going to go back to here. So your homework is, go back to our Canvas page. You have to watch a movie and it's called Flatland. Has anybody read the book Flatland? There's a book, right? Flatland. Anybody read it?
Is that like the Bible for flat earthers?
What was it?
Is it like the religious texts for the flat earthers?
No, no, no. That's funny. Can you guys still see my screen?
Yes,
Okay, can you see me searching for Flatland, the book?
totally.
Okay, cool. All right, so Flatland is a book written by, actually, it's a little bit misogynistic. I'm sorry about that. So just ignore that if you can. I'm sorry. But it's actually, other than that, it's got a lot of really fun things. And then the movie, and Flatland is one movie, and then there's another movie called Sphereland, but don't worry about that. Just worry about Flatland. If you want to watch that one, that's fine, but this is the one that I'm asking you to watch. But Flatland is a romance of many dimensions. It's a novel about these people that live in 2 dimensions. They live in a 2-dimensional world. And so here is, this is a home of a house in Flatland. And you can see the men's door and the woman's door. I mean, this is a little bit, sorry about that. I apologize in advance. If you're a woman, please just ignore the misogynistic parts. But it's interesting, and maybe historically, just to be aware that women were not considered equal to men. Oh, not even 100 years ago. This is bizarre to me. It's unbelievable. And so we're reading this book not for that part, but for the concept of living in 2 dimensions. There are some interesting parts though. So even though I'm going to ask you to ignore the idea that women are lesser, I want you to think about what the women are in this story, and therefore, you know, learn something about this dimensionality. So anyway, so there's this movie. Oh wait, I wanted to go back to that. I wanted to go to the actual assignment. So watch this movie and then take this quiz, okay? You get 3 tries, so hopefully by the end of the 3 tries, you get all the questions right. It's worth 10 points. Okay, actually should be worth 15, but whatever. I don't know, doesn't matter. It doesn't matter, it's all the same, okay? So you watch a movie, it's about an hour and let's see how long it is. An hour and 40 minutes, okay? And it's pretty funny, and it's really important that you watch it before the next class so that we can talk about it. And it's really going to give you some fun ideas about you and I. We live in 3 dimensions, right? We live in 3D. But the goal is when you read the story, but the Flatlanders live in 2D, right? And so when we ask the question, what would it look like to a Flatlander if they went to 3D? You understand the whole point is for us to ask the question, what would happen if we could step out of our 3-dimensional universe that we perceive into 4 or even higher dimensions? And so next class, I'm going to ask you to start thinking about the concept of space and time. And I'm going to do a little bit of a mathematical job with you. I'm going to start with 0 dimensions, which is a point. I'm going to go to 1 dimension, which is a line. 2 dimensions is a plane. Okay, and I'll do that on what's today? Today's Wednesday. I will do that next week. Okay, on Monday. All right. Any questions about that? You guys know what to do? You're going to watch a movie and take a quiz. Any questions? Okay, so you do have a participation quiz that I'll be putting up, and I have about half of the quiz written right now, and I still have to write a few more questions, and it'll be based on our discussion today, anything we talked about, and I'll have it up for you in about an hour. Okay, so I will see you guys next week. I'll see you next Monday. Okay, please watch that movie, Flatland, and we will have a fun discussion on Monday. Okay, so have a great weekend or the rest of your week, and we'll see you later. Thank you.
Thanks, Professor. Have a great one.
You too. Bye.
Okay, Sean. Bye.
Bye.